All right, this is Erik Wegge for Lab 3 Part A, explaining my code for my thermocouple. So what it does is it imports a library which is saved in the same file that this Python script is running in, that contains the code that is able to interface with the analog to digital converter. Here, since I'm working with the thermocouple, I've chosen a gain of 16, which corresponds to a voltage differential of plus minus 0.256 volts. And what this code does is that until you tell it to stop, it calculates the value using that analog to digital controller library based on the gain that's put in. And it prints out down here the difference in the voltage between pin A0 and A1, and I'll show that circuit in just a moment. Down here is the rest of the code that calculates the actual voltage in microvolts and the temperature of the thermocouple. So here is my circuit. There's 5 wires that plug into the Raspberry Pi and the analog digital controller, and those 2 black wires right there connect to the thermocouple wire, type K wire, in there in the ice bath, approximately 0 C. Well, it's hard to get to 0 C, so about 1 degree C. Here's the hot water setup. I won't be displaying that though. So here is the soldered end of the thermocouple, if it wants to focus. There we go. So I'll grab onto that and then watch as the temperature should increase. Or maybe not. Oh, because I'm pulling the reference point out of the ice. But okay. Anyways, if I go ahead and put that in the water right now is about 75 degrees according to my thermometer, and you can see it's bouncing around between about 65 and 70 degrees C. All right, this is Erik Wegge for Part B of Lab 4. This is the code block for the thermocouple, same as Part A. Part that I didn't explain in Part A is actually this equation here to calculate the temperature. So this here is calculating the temperature of the thermocouple based on the value of the voltage across the 2 terminals, or across the 2 wires of the thermocouple. And I've used a regression equation here to calculate what it actually should be. So this should be the real temperature of the thermocouple in the water. So if I go ahead and I'm going to leave this in the water for just a little bit here, and what I'll do is I'm going to pull it out just to demonstrate what happens when you pull it out of the water. So it bounces around a lot. It's not very precise, it seems. Only about, I can only tell about 3 degrees C difference. So it's only ever like 71, 68, 65, 62, 59. It's never, within 70, 71, 72 ever, even though that thermometer is reading 71 degrees C right now. So I'm going to go ahead and pull this out and hopefully be able to keep this in frame while I reach behind me and pull out the thermocouple. And what should happen is that the temperature should drop now. Yep, 38, 32, 23. Yep. So this data, when I actually run the experiment, gets saved to a CSV file, which will be imported into Microsoft Excel in order to calculate the time constant related to the thermocouple. Yeah, that's about it for the thermocouple. All right, this is Erik Wegge for the Temperature Lab, Lab 4. This is the thermistor section for Part B. This here is the code for my thermistor, pretty similar to the thermocouple. The only big difference, well, there's two big differences. One is the gain value is set to 1, which corresponds to a voltage differential of plus minus 4.096 volts. And then down here, the difference between that thermocouple is how the temperature is calculated. So in order to calculate what the thermocouple or the thermistor thinks that the temperature is, an equation specified by the manufacturer for the thermistor has to be used. So, and it takes a resistance, it doesn't take a voltage. So the value for the voltage on the analog to digital controller or converter has to be converted into a resistance based on the circuit itself. So I'm using a 10K NTC thermistor with a B value of 3950. So the resistance is calculated with this equation, and then the false temperature is calculated as this, where the resistance of the thermistor is 10,000 kiloohms at 25 degrees C. That's 298 Kelvin. So this false temperature variable outputs a value in degrees Celsius. That's the conversion factor right there. And this right here is that B value. This here is the regression equation used after the thermistor was calibrated. And when I'm taking data, I usually write that data out to a file, which is commented out right now. So right now, this is measuring the voltage differential between A0 and A1 on the ADC, the measured voltage, the measured resistance, and the temperature of the water that I've got that in right now. So I'll move over to my circuit. It's running the thermistor from A0 out to here, the voltage divider, and then it's sending some of that current back to A1 through that yellow jumper wire, and the rest of the current through that 10K resistor down to ground. That's how. So the voltage that it's actually measuring is the voltage between A0 and A1. This here is the thermistor in water. Right now it's reading 62 degrees C. Over here it's reading, that's about 62 degrees C. It's a little off. It's not quite perfect, but close enough. So what I'll go ahead and do is I'll go ahead and pull that thermistor out of the water and I'll watch that drop. So it drops much more slowly than the thermocouple. That's just a property of how the thermistor is. But regardless, I only have to show this for a few seconds anyways, just to get the point across. So yeah, that is the thermistor portion of Lab 4, Part B.